So good afternoon, everyone. So after 1 week of a break, we are back again. And it's a really privilege for us. And we are also feeling great honor to have today's speaker, Professor Ganapathy Baskaran with us. And he is quite a well-known condensed matter physicist in India. And also he's highly acclaimed theoretical physicist all over the world due to his work on high temperature superconductivity, where he developed this resonating valence bond theory with Professor P.W. Anderson, Nobel Laureate in 1987-88. He is also known for his discovery with many other fields. One quite well-known field is emerging gas field theory in strongly coated system, which has opened the new field of research. And his other research interests lie in quantum Hall effect, strongly coated electron system, random lattice gas field theory, supersolid phases in helium-4, and many more things. Okay, so what I can tell you that by going through his profile, I found that he has contributed quite a lot in condensed matter theory, and many of the things are quite original. So as far as his academic background is concerned, he obtained his PhD degree in theoretical physics from Indian Institute of Science, Bangalore in 1975. And after that, he held several academic positions before joining as a permanent position. So you should read his very nice article recently appeared in Resonance and other, where he has described his journey, that it was quite a challenging journey at that time. So he held several academic positions like reader in physics department, University of Madras, visiting professor at ICTP, then research staff in Princeton University, where he got opportunity to work with the Professor P.W. Anderson before joining IMSc in Chennai as a professor in 1987. And at present, he is a Sir Distinguished Professor in IMSc. Also, he is associated with IIT Madras and Premier Institute of Theoretical Physics, Waterloo, Canada. There are several feathers in his cap, as you might have got to this point. He got the ICTV first award in 1983 for his important contribution in antiferromagnetic insulator, phase transition, condensed matter, and lattice gas theory. He is also awarded Shanti Swarup Bhatnagar Award in 1990, and he is a fellow of Indian National Science Academy, New Delhi, Indian Academy of Science, Bangalore. So really, it's again, we are quite lucky to have him here. Since long time after demise of Professor P.W. Anderson, we are looking for some speaker who can basically give some summary about the work of Professor Anderson, who invented the field called condensed matter theory. And who can be better than Professor Baskaran, who basically has a close association with Professor Anderson. So without any delay, now I would like Professor Baskaran to deliver today's physicist colloquium on quantum matter and P.W. Anderson, 1923 to 2020. And with this, I hand over the floor to Professor Baskaran and invite him to deliver today's colloquium lecture.
Thank you, Pankaj. I will try to share my screen.
Window. PDF. Share. Slide 2 from current slide.
Pankaj, is it visible?
Yeah, it's visible.
Okay, wonderful. So thank you, Pankaj. Thank you, Saurabh. And thank you all friends for inviting me to this colloquium. I really feel honored and happy to be talking to you. I would have liked to be there personally and see the great campus and the great Brahmaputra. I have been to Guwahati twice or thrice, I don't remember exactly. So I really hope to come again and talk to you personally and discuss physics. So it's really a pleasure to be talking to you. So today I will be talking about quantum matter and P.W. Anderson, who lived for 96 years, full of life and enthusiasm and contribution. So this is going to be my... So I have to acknowledge various agencies for supporting me even after superannuation, SERB and DAE. And then since last October, I'm closely associated with IIT Madras as a distinguished professor. And since last 10 years, I am associated with Perimeter Institute. And of course, I have been at Math Science since 87. So I thank all of them for supporting my research and so on. So my connection to Professor Anderson started through Professor N. Kumar, late N. Kumar, and my guide K.P. Sinha, my good friend Rajaram Nityananda, late Professor S.K. Rangarajan, Rio Tosati, Patrick Vazreka, Srinivasan, P. Ramakrishnan, and others. So today what I'm going to do is a walkthrough, kind of, I have no clear agenda. I will talk about quantum matter, of course, as perceived by Phil Anderson. And I will talk more about Anderson because it's an inspiring story. So this is Anderson. Just he's standing at the big window in his office. That's a roof garden. So I took this picture in 2012. Okay. So I will tell a brief history about Anderson, and then the style of doing science, is a role model, and how he catalyzed several Nobel Prizes, supporting young people, 7 decades of resonance with quantum matter, and his famous article, More is Different, and how temperature superconductivity is different, and how beyond physics, he was against Star War, nuclear arsenal proliferation, and so on. So I will tell all these things. And before I begin, I have to acknowledge your effort to keep the science going, because it's very important to keep the science going. Of course, people are suffering and there is innumerable problems for common people. But the little science we do, I'm sure will help society in the long run. Now, let me start with a very famous beginning of a famous poem by William Blake, who says, "To see a world in a grain of sand, and a heaven in a wild flower, hold infinity in the palm of your hand, and eternity in an hour," and so on. Now, it's relevant now because as scientists, we attempt to comprehend essentially the infinite nature and the universe as much as possible, using our earthly experiences limited by space and time. We look at nature, we walk on the earth, we analyze some materials by experiments and through the telescope, but we have unlimited imagination. So that's how science begins. So it fits with William Blake's poem. So we are looking at tiny things. We are an infinitesimal in the history of the universe in terms of our lifespan and our size. We are. But amazing human beings in the earth has been able to achieve so much in the last few centuries in terms of understanding nature. And hopefully we'll make good use of it and evolve into better beings. So just to give an idea about how quantum matter comes from a very humble beginning, burning coal, which is an example of a black body radiation, gave clue to our fathers that if you look at the intensity as a function of frequency of the electromagnetic radiation, instead of the curve that you expect, a classical curve, you find a maximum and then it comes down. So it could not be explained by whatever we knew in 1900. So Planck decided to fit it to a distribution. In the process, he introduced called the Planck's constant. It's an amazing insight. That's how nature revealed its quantum secret to us back in 1900. Now, there is no return. Now, again, from humble beginning, Einstein looked at specific heat of diamond or sodium chloride, any ordinary material, and then found that there are deviations from Dulong Petit slot low temperature. He said it should be quantum mechanical. So he began what we call as quantum theory of solids. And similarly, others looking at heat capacity of electrons in metals found linear specificity at low temperature. People like Pauli Sommerfeld rationalized it by using the then developing quantum mechanics, using Pauli principles and so on, introduced the notion of Fermi C, and it explained things remarkably well. So a very simple experiment that we do in the lab, calorimetry, gave us insight about inner workings of nature, quantum secret. Immediately, young Chandrasekhar, sitting as a student in Presidency College at Chennai, former Madras, or currently called Madras, currently called Chennai, it used to be called Madras. So he used it properly in the context of stars, and then there is a famous Chandrasekhar mass limit. There is a recent example of deep understanding from helium droplet, a nice article by Waterloo. I will refer to it later, the recent archive. Now, we all know matter is quantum. Whether you take a piece of rust, or a grain of sand, or a drop of water, or a paisa coin, each one of them contains so much quantum physics, so much deep insights into nature, which is what I will describe. Suppose you take a piece of iron, it's a ferromagnetic metal. The magnetism originates from the electron spin, which is relativistic and quantum mechanical. So if you look at the piece of iron or a magnet, you should be reminded of relativistic quantum mechanics at work at macroscopic scale. Similarly, there is something called double exchange, which Zener started and Anderson Hasegawa flourished it. So if we take rust, very common phenomena, it's supposed to be Fe2O3. It has some water molecule. When it heated, the water molecule goes and we are left with hematite, which is a Mott insulator. Mott insulators are different from ordinary band insulators in the sense, while electrical currents cannot flow, it can support spin currents very easily. So in some sense, spin degrees of freedom are active, charges are not active. While it's easily described, its theory is very beautiful and many, many wonderful things. Now, if you take a grain of salt, the sand, geologist will tell you, he tells the history of the place, millions of years ago, and so on, how the grain was shaped. And there are many minerals, and parts of it are amorphous and a glassy material. If you take a drop of water, you see electric dipoles, there is paraelectricity or quantum paraelectricity, and there is some quantum physics there. And then if you take a paisa coin, it's supposed to be copper and other alloys, so there are magnetic impurities. Then if you take a compound of copper, for example, cuprate, you get superconductivity. The one that I have circled are the one responsible for Anderson's Nobel Prize. Anderson gave some model for phenomena in amorphous material, and also for magnetic impurities in metals, and he got Nobel Prize. Just analyzing very simple things. I hear some background noise. Maybe everybody should mute. Okay. And Anderson is a model to follow because if you look at his scientific history, there are so many models in his name. Spontaneous symmetry breaking. There's something on Anderson Tower. There's a very simple quantum rotary model, double exchange. Anderson impurity model for local exchange, local moment formation, which got him Nobel Prize. Anderson localization, again Nobel Prize. Spin glass, superfluidity helium-3, RBB theory, normal state of cuprates, emergent gauge fields. So many. In fact, it's not a complete list. So I'm going to talk about this gentleman. He was born in 1923, and he grew up in a farmland in Urbana, Illinois. Because his dad worked as a professor in Urbana-Champaign. His grandfather was a farmer. So my parents belonged to a group of warm, settled friends whose life centered on the outdoors, and in particular, in the Saturday hikers. My happiest hours as a child and adolescent were spent hiking, canoeing, vacationing, picnicking, and singing around the campfire with this group. They were unusually politically conscious for that place and time, and we lived with a strong sense of frustration and foreboding at the events in Europe and Asia, because that was the period of war, World War. Undergraduate studies and PhD in physics at Harvard. Graduate school, according to him, consists of excellent courses, a delightful group of friends centered around bridge, puzzles, and singing. So PhD students at IIT Ganapathy, you should be happy. You have good nature. So enjoy the nature, at the same time do your science well. Joyce became his life partner, and Anderson had 73 years long life journey with his wonderful wife. They were a wonderful couple and great hosts. Joyce was a great support for Anderson. Their daughter Susan was born in 1948. Susan is a great artist. Undergraduate studies in, so this is the couple. And Anderson lived about 15 miles away from Princeton. They had their house in the middle of a 10-acre small estate, which was individually maintained by Anderson and Joyce. There were no workers. Joyce used to work for 4 hours in the garden. Anderson used to work as 2 hours in the garden. Probably that was the secret of his health and longevity. And then come to the office and do his physics. So I have visited his place several times. So this is one such picture during the fall. That was in 2009. Now Anderson, after completing his PhD at Harvard, joined Bell Labs. And then he had a joint appointment with Cambridge very soon. Then moved to Princeton in 1983. Then during these periods, he spent a month at Cornwall in UK. In that time, he used to just take it easy completely. No email communication, no telephone communication, enjoy nature and think about nature. So he worked in Bell Labs, which is a well-known place for young people who may not have heard about it. He got 9 Nobel Prizes and 4 times Turing Award. And a transistor was born there. We are all enjoying the benefit of that. And 3D background radiation, a stamp for Big Bang Theory. And the fact that Planck's constant was there at the beginning of the universe was discovered from Bell Labs. It's a great place. So he says his Bell Labs influenced him a lot. So 2 of the mottos at Bell Labs was get the best people in the world and get out of the way. Theory should be on top, not on tap. Now Anderson was very humane person, very conscientious about humanity and human beings. So he was against war, Star Wars, nuclear proliferation. He even went to the Senate and gave testimony, criticized the government for doing various things. Okay. Now, just to tell about Anderson's character, I will narrate an incident. I was sitting in his office in 1986. A young undergraduate student walked in. Students knew that no prior appointment was necessary to meet this Nobel Laureate at his office. The student elaborated on an idea he had. Anderson noticed my growing impatience. He, however, patiently listened till the end. After the student left, Anderson enlightened me with his own understanding of a very important point that the student was actually trying to convey, but did not succeed. That awakened me. So, on several occasions, Anderson brought out deep meanings in very ordinary sounding seminar talks and pleasantly surprised the speaker and audience. It was said that Anderson's presence made a difference to conferences, workshops, and schools. He alerted colleagues about key developments, reported in the meetings, and shared his ideas liberally. Well, this is again a hilarious story. During my stay at Princeton, I had a visa problem, small glitch in the second year. Anderson came to know about it, and he came to my office and told me that I will call George Shultz and fix it up. George Shultz was Secretary of State of the US government and a Princetonian whom Anderson knew personally. I felt elated, but politely stopped Anderson because I thought that George Shultz can be made use of to stop China-India war or some bigger things than my visa problem. So the particular problem got sorted out by a secretary, but secretary at physics department, efficient secretaries. So the third year at Princeton became a memorial period in my scientific career. So while Anderson is like this at a personal level, people outside call him as a gruff person, a very tough-looking guy. So in a Scientific American article, John Horgan writes that Robert Schrieffer, a Nobel Laureate in physics, who had often butted heads with Anderson, admires his blunt style. Schrieffer says Anderson has played a uniquely provocative role to make sure that people get things right. But he adds that Anderson can be undiplomatic. Anderson was usually surrounded by young people during meetings, lunches, etc. He was truly international. He was of the belief that scientists and students are messengers of peace. So this brings me, so how I got introduced to Anderson's work. It's a very interesting story. Back in December 1970, there was DA symposium in Madurai, my hometown. So I had joined as a PhD student at IIT Bangalore. So I listened to two talks, one on so-called Majumdar-Ghosh model, which had some connection to valence bonds, and then spin fluctuation theories by T.B. Ramakrishnan. So that was the first exposure. Then back in IIT, N. Kumar taught me Mott localization, Anderson localization, supersonic helium, super exchange theory, Rajaram Nityananda, S.K. Rangarajan, group discussions, and so on. So I had a full exposure to Anderson's thing. Then there were schools. Shastri introduced me to various aspects, Chandra Verma, H.R. Krishnamurti. Then I used to run a journal club when I was a student, PhD student and a postdoc at IISc. Exclusively using Anderson's paper. Whenever they came, either I will review it, journal club, do journal club, or my friends would do it. So I had a dream and so on. Okay. Now, I will describe how I met Anderson first. And also in the process, tell the respect that Anderson had for internationalization of science and how science is important for all humanity. So what you see is a beautiful landscape. That's where International Center for Theoretical Physics is located in the Riviera, on the foothills adjoining the river. And Abdul Salam, you all know, a great man, a Nobel Laureate, he thought science is important for developing countries. So he worked hard to establish an international center. And he got the help from his friend Paulo Buzinic, who talked to the local mayor and convinced him that it's worth giving a piece of land. So that's a piece of land where ICTP started. Currently, Atish Dabolkar used to be a TFR, is a director. It's a great place. So my meetings and in fact, during the late 70s, that played a very important role in the development of theoretical physics in our country. Now, of course, we are very matured. We have a lot of activities. But 50 years ago, it was very useful. So now, Anderson was a good friend and supporter and visited ICTP as whenever he can. And he talked to young people. And Eriot Rosati, a good friend of mine, recently he got Spirit of Salam Award. Eriot Rosati and M.S. Narasimhan of Tata Institute. They have shared the award. Very deserving candidates. So Anderson gave a colloquium. Eriot Rosati, who knew Anderson, being very shy and intimidated. Then Arun Jainawar, my good friend from IOP, he was there at that time as a young visitor. So he accompanied me and I had a 2 hours discussion with P.W. Anderson. And then I was at Princeton next year. It was a wonderful chance. So we had a nice college on superconductivity. In fact, Anderson came as usual. He gave good talks. John Goodenough came. And he also gave 1 week of talks. You may know John Goodenough got his Nobel Prize last year at the age of 97. And no stopping. He's still very active and going strong. So this is a scene where Phil Anderson is talking with my former student Muthu Kumar, Manas Sardar, and Indrani Bose, and then my colleague Mukul Lal. So he's very fond of students. And then he also came to India and to Nepal, because there was something called the BC Spin School. Bangladesh, China, Sri Lanka, Pakistan, India, Nepal. Students used to come. A team of international people will come and give lectures. This was started by Jogesh Pati, Eriot Rosati, and supported by P.W. Anderson. Very good way of bringing people together in this region. And it worked extremely well. And Anderson was very supportive. He came a couple of times, but unfortunately it stopped. Now, this photograph, Anderson was struck by the beauty of the Himalayas in front of him. So he didn't care about the dirty floor. He just fell flat on the floor and enjoyed. When my student took picture, he said that, please put a caption, physicist at work. That's the way Anderson works. He enjoys nature and works. Now, while talking about these things, I should also point out about the institute I'm associated with for the last 10 years, Perimeter Institute, a great place where Stephen Hawking was also there. Now, it's again a respect for science and importance of science for progress of society from an individual, namely Mike Lazaridis, who started his BlackBerry company. He gave $150 million as an endowment to begin this institute. He has given totally nearly $500 million. There are examples like this in our own country: Tata, Birla, Aragappa, A.C. Mutaya, Infosys Foundation, Krish Gopalakrishnan, Shivnadar, Shastra, and so on. So it's very important for young people to recognize that supporting science will be helpful. So if you have a rich uncle, please convince him to spend part of his billion rupees or dollar for science. It will take society a long way. Now, I have not come to quantum matter. That will be a small piece at the end. I will tell about how Anderson generously planted seeds for Nobel Prizes. There was a meeting in Aspen honoring Anderson's 50 years of contribution to condensed matter physics in 2000. So it brought several collaborators. Two people spoke. I also spoke. I will come later. Doug Asheroff, he got Nobel Prize in 96. Dan Sui, Nobel Prize in 98. So what Doug recalled was that he had seen some glitches in his study of helium-3 liquid, and his guides told him that it's something, ignore it, it's some experimental artifact. Anderson looked at it carefully and told him that please continue to look at it carefully because we have predicted superfluidity in helium-3. So he went back and did his experiment carefully, and he got Nobel Prize. So I have met Doug Asheroff several times, including once in Anderson's house. So I remember when Doug got Nobel Prize, that year I was at Princeton. So Anderson came running to my office, essentially jumping with joy, saying that, oh, Doug got Nobel Prize. Then it's a case of Dan Sui. Dan Sui was electrical engineering department. He was trying to repeat von Klitzing's integer quantum Hall effect in a better sample. And in the process, he found out some developing plateaus between integer Hall plateaus. So he didn't know what was going on. So he went and showed the data to Anderson. Anderson looked at it for a while and thought about it. And he said that, please continue. It should become sharp. Please continue. So it became sharp and got Nobel Prize for fractional quantum Hall effect. So Anderson has deep insights into experiments. And story of Josephson effect is also a marvelous story. Anderson, I told you, had some joint appointment with Bell Labs. So he was giving a course at Bell. There was a bright student sitting in his class, young Brian Josephson, an experimental student, physics student. Anderson said that if you have two superconductors which are weakly coupled, there should be some spontaneous current between them, which will be a periodic function of the phase difference based on some very general argument. And then this was his intuitive conjecture, and then he forgot about it and rubbed it off. Young Josephson took notice of this statement and went home and seriously worked out and derived that what we call as Josephson relation and showed it to Anderson. Anderson was thrilled. He said, oh God, my conjecture was correct. Go ahead and publish it. But nobody will publish it. It was rejected because nobody believed it, including John Bodine. So what Anderson did was, in a very positive way, he went back to Bell Labs and joined hands with the experimental colleague John Rowell and performed experiments and demonstrated that Josephson effect exists. So thereby removing a widely prevailing skepticism in the community on the possibility of such effect. Rest is history. Josephson was awarded Nobel Prize in 1973. In fact, there is a Physics Today article about this history by Anderson himself. You may like to read it. So this is Anderson. This picture was always hanging in Anderson's office. When I asked him way back in the 84, who drew this? He said it's one of my friends from Bell Labs. He gifted it to him, this cartoon, on his 60th birthday. But he told me the name, I forgot. Recently, Anderson also forgot. So we don't know the author. I wrote to several of Anderson's friends. Nobody claims that they drew this. So this is a picture. I have used it in some of my articles. So it's a very illustrative picture of Anderson's style of doing it. He plants a seed which grows into mountains, and so this depicts each part of the picture depicts about Anderson's contribution. I will come to it later, maybe. So this is sorry, I am okay. So the same meeting I told you that where Doug Ashraf and Dan Suyu spoke about their Nobel Prizes. As a old collaborator, I was also asked to speak. I told them, the audience, that I'm going to reveal the secret of Anderson's success. Anderson was in the audience and he raised an eyebrow. I said that Anderson kept looking at a body of experimental results and communed with nature till he found the right model. Everybody knew this. My next sentence surprised the audience and got a smile from Anderson. That was this. While everyone would try to solve his or her model using mathematical methods, analysis, approximations, etc., Anderson would go back to experimental results. Experimental results guided him to guess the right solution to the right model via physics-driven mathematical analysis. In fact, Anderson laughed. Later, we had many, many discussions about that style of functioning. Anderson also believed in importance of thinking in generalities. He told me that while he was at Bell Labs, Bill Shockley was his boss. So he asked him to do some detailed calculations about barium titanate. Bill Shockley had a pet theory, but Anderson said that I became more interested in generalities, feeling that calculations were premature. This is an important lesson in doing science. While acting locally, one should not forget to think globally. Once he remarked to a friend of mine, the problem is you start calculating before you start thinking. So I recently got this quote in an article. These are all, two quantum chemists. They say, give me insight, not numbers. The more accurate the calculations become, the more the concepts tended to vanish into thin air by Mulliken. It's only because we accept the risk of error that we can reap new discoveries. René Thom. So, I'm not saying that numbers and calculations are important, but they have their places. So if you read Anderson's many essays, it becomes very clear how we have to combine both. Concepts should emerge from numbers, and then you should give numbers, and there should be a feedback. If you look at Anderson's very first PhD work, Theory of Line Shape, was inspired by some experimental results of NMR line shape. So the line had a peculiar shape, some width, so he did some quantum mechanical calculations, and that became a famous Anderson-Kubo theory. Spontaneous symmetry breaking, look at quantum magnets. Super exchange, looking at a body of oxides. Double exchange, looking at, again, oxides and ferromagnetic metals. Soft mode theory, by looking at various ferroelectrics. Frustrated spin system, looking at a lot of spin glasses and so on. So I should also point out at this point how well-known Anderson was even at his young age, how well he was respected. BCS theory appeared in the scene at the end of 1957. It caught the attention of young Anderson, who was worrying about magnetism, many-body localization, later called Anderson localization. Then Ted Schultz, he was at IBM, Steve Schultz Matisse theory, for example, same too, a good friend of mine is no more. He told me the following story in the summer in 1987. Bardeen-Cooper-Schrieffer theory had just come out. It was getting a lot of attention, but not completely accepted yet, partly because of the gauge invariance issue. News of BCS theory reached Pauli, the famous Pauli principle, Pauli in Switzerland. He was quick to ask what young Phil Anderson felt about it. The answer was that Phil Anderson was excited and was working on it. Pauli is supposed to have remarked, then BCS theory must be right. It's amazing. From BCS theory to the mass of elementary particles, it's a great story you all know, so-called Anderson-Higgs model. There is a very delightful article by Ed Witten in the book called PW 90, A Life of Emergence, commemorating Anderson's 90th birthday. There are many articles, including my own articles. There are lots of pictures, so you may like to see. So Ed Witten describes very beautifully the history of Anderson-Higgs model, how insights into superconductivity, deep insights, gave you clues about origin of mass of elementary particles like quark or electron. Amazing. So there's a small story. I was visiting Anderson. See, I made the point to visit Anderson for a week every year. I have been doing it religiously till 2018. Last year, I did not go, unfortunately. So in 2012, I spent a week. So it was 3rd July. News had come to physics department, Princeton University, that CERN has, the LHC has seen Higgs particle, and they are going to announce it officially tomorrow. So the whole department was jubilant. They said, our Anderson-Higgs particle has been discovered. So I took a photograph with Anderson. My friend Fuan Ang took this photograph. So it's a memorable day. And I want to tell you what Anderson told me. So it was 3rd July. I was, okay. Anderson told me, I'm happy for Peter Higgs. His mind instantly shifted to physics. He started asking, is Higgs field a collective mode of some Fermi? Has this CERN determined spin and another quantum numbers of the Higgs particle? Physics kept Anderson busy and happy till the very end. This was his reaction, He didn't talk about Nobel Prizes and so on. He said, I'm very happy for Peter, and then started asking questions about deep physics that should follow from this Higgs discovery. So there are many things, Anderson's theorem of dirty superconductor. Again, he looked at a collection of superconductors, alloys, and found some regularities. The superconducting transition temperature did not vary very much. Lately, there is something called, some of the young people working on superconducting may like to look at, called high entropy alloys, where again similar phenomena takes place. In spite of disorder, the TC doesn't change very much. Anderson synthesized it into a very simple theory, which became known as Anderson theorem of dirty superconductors. Again, came from experiments. The notion of Coulomb pseudopotential with one of his former students, and the local magnetic moments, Kondo effect, RG, Anderson, everything came from experiment. And a very beautiful theory after Anderson localization called the scaling theory of localization by the famous gang of four, T.V. Ramakrishnan, Licciarello, Abrahams, and Anderson. It's a beautiful theory. I recommend you to look at it, which has its ramifications even now into quantum computers, issue of decoherence, and so on. Again, Anderson did many things in helium-3 and RVB theory of superconductivity, emergent gauge field, normal states, and so on. Then, this is just an advertisement. While working, I was fortunate to be working with Phil Anderson. So we discussed pseudo-fermions, pseudo-Fermi, enlarged Hilbert space ideas, which is already there, and then emergent gauge fields, quantum spin liquids, and so on. So this is a picture I am very proud of because, see, I was at Aspen. Again, I want to make an advertisement. Aspen is in the hills near Colorado. In the winter, it's a ski resort. In the summer, it's a beautiful place. There are bees. It's a music place. There are lots of music in the background. And Aspen Physics Center is located there. Apparently, a graduate student, a PhD graduate student from somewhere in the US, convinced his rich uncle that he should give a piece of land for supporting physics. And that's how Aspen Physics Center started. Again, I request young students and others to convince your uncle or your father to support physics and basic science. It's worth it. So I was visiting Aspen and enjoying the nature, listening to music. And then suddenly an inspiration came to me. I saw some bees running around. So at that time I was working on RVBs. So I wrote RVBs and drew this sketch. So bees were running between flowers and collecting honey. So I was I was married and I had children and so on. Instead of thinking about my wife, and I looked at the flower, in fact, her name is White Rose, I started thinking about d orbital. So some of the flower petals look like 2p orbitals and d orbitals. And then big flowers look like some aromatic ring compound. So I sketched this and said that bees will go home, which is a honeycomb lattice, which is graphite. And that's where RVB started. So I sent this sketch to Anderson. And he was very happy. In fact, the very next week he gave a talk somewhere. He reproduced my picture and made a comment about this and so on. So that's why I just want to show you my excitement with RVB. And okay. Now, again, in a very simple concept, which summarizes many deep things in a very nutshell, you all know that if you have 4 spins which are coupled antiferromagnetically, they can go to a very simple ground state in which every bond is happy. Now, if you have 3 spins, as you can see from the picture, 2 spins are unhappy. Depending on the configurations, any pair of spins will always be unhappy. This is called frustration. Now, frustration is part of life. It's part of nature, part of economic market and so on, because there are many elements which are competing. So, in order to synthesize this in the context of interacting spins and frustrated spin, Anderson and Edwards wrote a model called, a famous model called spin glass model. And now it has become a paradigm for models in neuroscience and so on. So I will not go into the detail. It's a wonderful development which went beyond physics. So the construction of new algorithms and computational schemes for hard combinatorial optimization's problem, new analytical approaches to finding bounds of costs of near optimal solutions of NP-complete problem, models of protein folding and conformational dynamics, maturation of the immune system response, prebiotic and biological evolution, neural networks, new methods of neural-based computation, science of complexity. Look at it. A piece of metal, namely copper, containing a tiny density of manganese or nickel. So the spins are randomly arranged. So depending on the separation, they have ferromagnetic and antiferromagnetic coupling. They don't know how to order. So there's frustration. Anderson synthesized the famous Edwards-Anderson model, Anderson and Edwards. And it became a beautiful model. And that's the basis of Hopfield's neural network and many, many things. So it's very important to construct model whenever possible. In that sense, Anderson is a model to follow. Now, in the rest of the time, I will spend a very insightful article that Anderson wrote called More is Different. In fact, it was a reaction to high energy physics friends, because at that time, for some time, people were feeling that to understand standard model or quarks or quantum gravity is more basic than anything else. Rest is chemistry. In a friendly way, they were used to make jokes and so on. Now, Anderson thought deeply about it, and he said, actually, science is different. So he made this very nice article, More is Different. The title is Broken Symmetry and the Nature of Hierarchical Structure in Science. There is a very delightful article, commentary on this by our friend Rajaram Nityananda, who is at Premji University, Azim Premji University at Bangalore. He was director of PFR Center, Radio Assistance Center, and so on, GMRT. So he has an article in Resonance where he comments on this work of Anderson, More is Different. And the same issue of reference, which I encourage students to look at every month, also has a special issue on Anderson. There are articles by T.V. Ramakrishnan, C.N.R. Rao, and myself. Okay, what does Anderson say? He says, the role of emergence and hierarchical nature of science in general and physical sciences in particular. He emphasized that what is at work in most of natural world and science is emergence. Hierarchy of new properties, surprises, and complexities emerge at each energy, length, time, and other relevant scales. This is how science gets created. In this process, the web of science and the grand unity also reveals itself. Unexpected connections, like I said, specific heat of copper metal, Arrhenius specific heat, Pauli principle, Fermi gave idea to Chandrasekhar about stability of stars, where gravitational pull is balanced by Pauli pressure. So unexpected connections. So, sorry. So he said, in science, we attempt to reduce things. That's very important. It's accepted without question. The reductionist hypothesis does not by any means imply a constructionist one. That means, given the laws of quantum mechanics or the rules of the game, it's not obvious that we'll be able to predict the outcome. So there is emergence, hierarchical. I will illustrate with a few examples. This was Anderson's point. So he said, for example, if you look at the two columns, solid state physics or many body physics depends on quantum mechanics that came from radiation, elementary particle physics. And chemistry depends on many body physics. Molecular biology depends on chemistry. And the cell biology depends on molecular biology. Psychology depends on physiology. Social science depends on physiology. But this hierarchy does not imply that science exists just applied wide. At each stage, entirely new laws, concepts, and generalizations are necessary, requiring inspiration and creativity to just as great a degree as in the previous one. So he says physiology is not applied biology, not a biology applied chemistry. So Anderson takes, in the context of condensed matter, or in the context of physics, broken symmetry, how it sets a ground for new phenomena, how hierarchy emergence. So I will illustrate it with my own example, which I, So this is, there's an article in the book edited by by my friends about graphene. So now this picture shows you a kind of block diagram. So if you take carbon atom, we don't know what's going to happen. You put carbon atoms together, you get a diamond, which has its own property. It's a good insulator, very expensive, and so on. Then you can form carbon nanotubes. So there is sp3 bond, there is sp1, there is sp2, sp1, sp3. Now let's take graphene, which is a pure sp2. So that's where the graphene world. And if you look at it carefully, how a new world emerges. For example, just by telling you what is sp3, you cannot tell there will be composite Fermi C. Because sp3, which is a symmetry broken state of a honeycomb lattice, so translation symmetry is broken. So that comes from because of sp3 bonding. So that immediately gives you a sigma bond and pi bond. If you look at carefully the pi bond, there is a famous Dirac cone, which people like Girish Shetlur and Saurabh Basu are all worrying about, and many colleagues and department doing experiments in theory. I'm sure experiments like Srinivasan are worrying about it. So then if you go to the edges, you see flat bands, and magnetism. Then you come down, this Dirac cone gives you possibility of two-channel Kondo effect. Then there is a chirality of wave function, and there is anti-localization. And then there is a parity anomaly, which is one of the crowns, one of the jewels in the crowns of field theory, realized in a very mundane graphene, and so-called spin Hall effect. And then go to this side, you see a careful analysis can tell you, demonstrate by doing a tabletop experiment, Zitter-Bohm that was predicted way back in the context of relativistic electrons, which will need enormous effort to see it in colliders, whereas you can see it under the same phenomena, similar phenomena, and the Klein tunneling, and the work with my colleague Shankar and Vinu Lucas, that you can realize Kaluza-Klein paradox and vacuum collapse and so on in graphene. So similarly, if you take Pauling's RVB theory, you go to spin one collective mode, fractional quantum Hall states, Landau level, room temperature quantum Hall state, composite Fermi C, and possibility of room temperature superconductivity. You notice just from one symmetry breaking, carbon atoms combine to give you a symmetry broken state, namely a honeycomb lattice of connected carbon atom. Just from there, so many profound things follows. So in fact, one can take water alone. According to Niels Bohr, he is supposed to have said that take hydrogen or oxygen atom, you cannot predict turbulence. Took hydrogen atom and one oxygen combined to give you water molecule. Now there is no hydrogen bond. Put few molecules together, there is hydrogen bond. Put more of them, there is water. Then put more of them, there is viscosity. Then there is turbulence. So physics is full of emergence. In fact, this is the one that I was referring to earlier. There is a nice article by Waterloo, which he posted in the archive very recently. It's an elaboration of his famous book, Universe in a Helium Droplet. They just take helium-3 superfluid, which happens in millikelvin scales, and there is a spontaneous symmetry breaking, and it's a quantum phenomenon. It's a symmetry broken ground state. By careful analysis, you can get analog gravity. You can get some physics of black holes, neutron stars, chiral superconductivity, cosmic strings, and all kinds of things. So just from a simple, that's one is reminded of the poem of William Blake. In a droplet, you can see many, many things. So this was what Anderson meant when he said, more is different. New phenomena do not follow simply by straightforward application of the underlying laws, and the theory often has to be guided by experiments. Science has levels arranged in a hierarchy from elementary particles to nuclei, to atoms to molecules, to complex materials on the one hand, and large biopolymers, cells, life, of course, a big jump, and onwards, even to, I don't know what is, human consciousness and so on. Okay. Now, I think I have about 10 minutes. I will spend the time because I was deeply involved with Anderson, the theory of high-DC superconductivity. I will not go into the theory at all because you can read about it, but I will tell the story. I was at Princeton at the end of, it was my second year. Anderson walks into my office, and I used to talk to him on a day-to-day basis, a variety of problems. I never cared about writing papers. He neither cared about it. So we enjoyed our discussions. Then one day, he comes into my office and puts a paper on my table and said, you should work on this, and left. On reading the paper, I got excited. Over a week, I developed a theory and presented it to Anderson. Anderson patiently listened and said, it's a beautiful but totally irrelevant theory for equivalent superconductivity, and left. I didn't feel offended. I thought I should take his remarks seriously. Then I continued to do my work. And mid-December, just before leaving for Bangalore, India, for a conference, Anderson said, your theory ignores spin-off mod physics, even though you drew my attention that it's a Mott insulator. That's an interesting story. I had a good friend, T.P. Radhakrishnan, who is a professor, senior professor at University of Hyderabad now in chemistry. He was a student at Princeton. So he brought to me, when I told him about Bernard-Muller's work on lanthanum copper oxide, the paper by Ganguly and Rao, and gave it to me. So I gave it to Anderson, which clearly said it's a Mott insulator. So his remarks made some subconscious rumbling in my mind, but I continued to ignore Mott physics. It was the first week of January. I waited for Anderson's return to Caltech from India and called him over phone. Before I started, Phil silenced me and said, I have seen the light. And I uttered 3 cryptic sentences. It was electrifying, and I too saw the light. And I said, I understand what you are saying, and will call you soon. I put my phone down somewhat abruptly. In 15 minutes, I called Phil and elaborated to him my understanding of his 3 sentences. He mumbled, you have smelled it right, absolutely. That was the beginning of our long collaboration on RBP theory of high-DC superconductivity. I will not, as I said, go into it, but I will come back to our last discussion in the next 5 minutes. But before that, I will also tell something very important about Anderson. People often talk about age and ability to be original and creative. Very often people say, no one does anything original after the age of 35 and the like. He says, this is a cliche. It's like a mean field theory. Wrong, wrong, wrong. Everyone has an age at which he stops thinking originally. He stops. If he wants, he can continue. But the age is enormously variable. I know plenty of others who haven't reached it till at 80 or more. So physics has remained exciting and wholly absorbing as a age. That's what Phil Anderson says in a book, refers to his book called More and Different. So there is a very nice article by Shobana Narasimhan from JNCASR on similar issue called Age-Old Question. I encourage you to read that article. So it's a common impression that as people age, their brain also becomes dull. That's not true. In fact, at least that's what I keep telling my professors, my directors at Math Science. I may be more than 70. Please give me some more time. I have more things to achieve. I have not reached my peak yet. Okay. Then how, in spite of the age. So this is a very interesting story. I visited Anderson in 2017. That year, there was a beautiful discovery from Tata Institute by Ramakrishnan's group and Anil Kumar and Tamilaved. They discovered ultra-low superconductivity in elemental bismuth. So I developed a theory and gave a talk about it at Princeton. Anderson listened to my talk, and as we were walking out, he told me, your theory is stupid. So I didn't mind his statement. I thought about it, why he says that. So in the next 2-3 days, I thought about his understanding of my theory. And after 4 days, on the day I am leaving, he told me, Baskaran, I yield. I understand you. You are right. I was very happy. Then he went to his corner of the room and took a model of a lattice structure, which is a structure of bismuth. And he told me that Vanier of Van function, he was Anderson's roommate at Bel Air, gifted it to him when he left for Seattle. So he gifted it to me. So I was very pleased. He was like 93 or so. Man is so sharp and fighting. So we used to have several fights. So this is the last kind of memorable picture for me. So I visited Anderson for a week in December. So he wrote to me saying that, Baskaran, I'm very busy this week, but you do come as usual, but I can spend only half a day with you. Okay. I said, I asked him, what keeps you so busy? He said, I have so many things to do for my friends. This friend got this award. This friend is celebrating his 100th birthday and so on. So he was very busy that week. I said, okay. So on the appointed day, Anderson came driving from home on his own. And I knew that was his 95th birthday. The department did not know. So I alerted the department that today is 95th birthday. So they were very happy. They bought a big cake and had a nice birthday party in this room. So we had a wonderful time. So at the end, when everybody left, Anderson and myself were chatting, and we had chatted about several things. What did we talk about? So Anderson has written a paper in May of 2018 called 4 Lost Conjectures. Philip Warren Anderson. I encourage young people to look at it. He was worrying about high temperature superconductivity. A lot, various aspects like normal states and so on, underdoped region. But he worried a lot about supersolid helium, which we discussed. We had a lot of concurrence about this, but difference of opinion. In fact, talking about supersolid helium, sorry, Chairman, how much time do I have?
5 more minutes.
So please keep talking.
Okay, thank you. So, I also wanted to check because there was pin drop silence. I was wondering whether I'm talking to myself. So,
no, it's going very fine. It's going wonderful.
Thank you. So, supersolid helium. I should tell an anecdote. See, Professor Narendra Kumar gave a journal club in 1970, I think 1 March or something, about a paper by Tony Leggett on the notion of supersolidity and its experimental implication. It was an idea that came from Andre Lifshitz and Chester, saying that solid helium-4 should contain some superfluid component because of large zero-point vibration and the so-called zero-point vacancy. They should delocalize. So it should have superfluidity property also. So Tony Leggett wrote a beautiful paper, how it could be experimentally detected. So Professor Kumar gave a beautiful talk. I was very impressed by that talk, so I worked very hard. And then Anderson's book came after a few years. There he challenged this idea of supersolid helium. So I didn't completely agree with Anderson. Okay. So when I met him in 1985 3s. That's the argument we have. I told him that I don't agree with Anderson, and I gave a variational argument in support of existence of supersolid helium-4. So he said, you are limited by your variational limitations and so on. But we had a good fight. But we had difference of opinion, but it was a healthy one. So when I went to Princeton, again we continued to discuss about helium-4 and several times. See, Anderson had a remarkable property that he always respected nature, and he was not afraid to call himself wrong. When Moses Chan and his collaborators found so-called supersolidity in helium-4, Anderson immediately changed his mind and he started supporting existence of supersolid helium-4. So that's why he used to. So he respected nature more than his own theory. There are several occasions. So in our last discussion, we talked about supersolid helium. At the end, he kind of, laughing and said, accused me, you are too imaginative. Then I told him that, Einstein says that it's better to be imaginative than something else. So he laughed and, that is, because he was kind of critical of some aspect of my theory. Okay, that was part of our last discussion. Then in cuprate, there are many regions in the phase diagram. We understand this over optimal doped region reasonably well from RBP theory point of view. But when you go to underdoped regime, there are lots of, in Anderson's own words, metallurgical complications. In particular, there is a phase called Nernst phase, and Anderson calls it as Hong's vortex liquid, and he has a theory, Anderson-Hong's theory. So still the community has not accepted and in a wholehearted way. So we discussed a lot about it. Then in trying to understand the normal state in the optimally doped region, so-called non-Fermi liquid regime, Anderson and Casey has a theory called hidden Fermi liquid. I keep telling people, there are 4 people who understand it. Anderson, Phil Casey, and my colleague Mukul Lad and myself. Because Mukul has written a paper, he's very fond of it. But nobody else believes it. But as usual, this theory is very pretty and very simple. People want complicated formalisms and so on. So we discussed about hidden Fermi liquid. Then the 4th one is kind of interesting. People in the field of cosmology, it's a big mystery. It again shows our ignorance about dark energy and dark matter. Anderson has a kind of solution for dark energy. He told me in detail, I didn't understand it. He told me, please go and talk to your colleagues. And so I did talk to my colleagues and they had some correspondence. So Anderson is very frustrated that the cosmology community, because he has Jim Peebles as his colleague, either don't listen to me or they don't understand me. I told him that, Phil, the latter is true. They don't understand me. You are not that easily understandable. So we laughed. So that was the thing. So, then let me end with this slide. So just before leaving, he remarked at the end of our long discussions on other topics also, Baskaran, you and I understand theory and mechanism of cuprate superconductivity in the optimally doped region so well. I wonder why others don't understand us. We laughed. And I said my last goodbye. So that's a picture. I'm very sorry. I am out of. Yeah. So this is at the end of our. I think we've discussed for about 2 hours or so. In fact, in between, Duncan Haldane joined and so a few friends joined, and we had laughter and so on. So it was a good time. So then let me finish with the last transparency. Anderson had several Indian people from Indian subcontinent, many people actually over years. T.V. Ramakrishnan, myself, B.S. Sastry, Krishnamurthy, Muthukumar, Muttalib, Sanjay Sarkar, Sudip Chakrabarti, Chandra Verma, G. Srinivasan, Rabin Bhatt, Anil Khurana, Sajeev John, Shivaji Sundi, Mohit Randeria, Nandini Trivedi. I'm sure I have forgotten others. and very senior people like Venki Narayan, who is at Harvard, C.K. Patel, A. Jayaraman, K.P. Sinha, and others were colleagues at Bell Labs. So Anderson made a very memorable visit to Bangalore during the valence fluctuation conference. And he tells me he was happy that he met C.N.R. Rao and Ganguly, because they had done experiments on lanthanum copper oxide, the parent Mott insulator. And they had a susceptibility curve as a function of temperature, which convinced Anderson of correctness of the RVB theory that was brewing in his mind. So it is after that he wrote the famous paper while returning to America. So this is the Indian connection. So again, I want to mention a small thing that about 10 years ago, I invited Anderson to visit India, because there are very many distinguished chairs of academy and so on. So Anderson said, Baskaran, I'm very happy to come to India and spend time at Chennai and at the beaches and so on. But I have many things to do. Particularly, I'm fond of some problems in biology. I am worrying a lot about it. So I have no time to think seriously about it. So if we go to India, 1 month will be lost, transit and so on. So he said, okay. And also Anderson was a long time foreign fellow of the Indian Academy of Sciences. So with that, I will close my talk. And thank you very much for listening, and I'll be very happy to answer questions. Yeah. Over to you, the chairman.
So thank you, Professor Baskaran, for giving such a wonderful lecture and taking us to the tour of a beautiful mind who basically seeded many things in the form of the condensed matter theory that we are witnessed for. And it was quite inspiring for students that they have looked at through your experience, and they will be certainly motivated to contribute in the direction. So with that, I would like to open the floor for the question and answers. So,
sorry, before I answer questions, you made a statement, beautiful mind, right? There is a famous Nash who got Nobel Prize for economics. There is a book on him called Beautiful Mind. And thanks to Princeton, I used to see Nash almost every day in the corridors. And then again, thanks to Princeton, Stigner was my neighbor for 3 years. All thanks to Anderson, I had a great opportunity to meet great people. And I should also tell, thanks to Abdul Salam, I met Professor Paul Dirac at ICTP once. Thank you. Yeah, anyway. Yeah, please go ahead.
Yeah, it's a time for questions.
Yeah, with the permission of Chairman, I would like to make one comment. It's not a question. First of all, I am thankful to Dr. Baskaran for giving a wonderful scientific life of Professor Anderson. And also, I'm very happy to see Professor Baskaran after 3 decades. I met him once in AMD College when I was a student. A professor gave a talk on superconductivity way back 1991. After that, I'm very happy to see the professor again. Same enthusiasm is maintaining.
Thank you very much.
Really, I'm very happy. Thank you, sir.
Thank you. Thank you. It's a pleasure.
So, Professor Baskaran, I just want to, add to that. It's an excellent talk given by you.
Oh, thank you. Sorry,
many of the things that were not known to us. So this that diagram that you have on graphene, that's a very, very informative page that I find where you have included everything that's possible there. So I actually would.
I can send you a copy of that article. And also, I forgot to mention that wherever there are stars, that's a contribution from AdSense, my colleagues here.
Okay. So among all these things, I mean, Anderson localization. Which one would you think? In fact, to the high energy physics as well, which we were not aware of. which one of the discoveries of Anderson you think really has, I mean, in your opinion, is all of them are of course superlative, but which one even among them stand out?
Oh my God. No, I think Higgs mechanism.
Okay.
Something
Anderson
very
Higgs.
profound. Anderson Higgs mechanism. Because, you know, if you look at his paper, he even makes a remark. That's the only paper where he uses symbols of relativistic quantum field theory instead of d by dx, del mu, and so on. And he makes a remark about the Higgs mechanism in the abelian context at the end. And the story is Anderson discovered the Schwinger mechanism independently, even though he was Schwinger student, he didn't know about the work. And Taylor later, energy physicist, connected it to Anderson's thinking. So he's very proud of that. Of course, you know, many things, you know, this is very difficult to say. If you go to your garden, so many flowers are there. I can't pick up, you know, the most beautiful flower. Many things are there. It's like, you know, just jokingly I say that whenever they find Miss the world, the most beautiful, you know, young lady, I tell them this is wrong. There are so many beautiful ladies all over the world. Sorry.
So one more last question. That is because you were there right from the beginning of ITC, and without looking at the DFT, you know, band structure of lanthanum copper oxide, would you have imagined that it is going to give you a very strong Mott insulator at zero doping? The decorrelations are so strong. Because I agree with Chandra Verma when he wrote that it could be a bad metal because it has one.
So again, let me narrate a story.
Electron.
Yes. So if you look at, sorry, I think the voice is getting cut. Do you hear me?
Yeah, we can hear you.
Okay. So see, Anderson, if you look at his early work on super exchange and so on, he basically went back to atomic orbitals or Wannier function and constructed simple Slater integrals and played with it and estimated U's and went a long way. I agree that things like LDA and DFT plus LDA plus U are very powerful and useful. There is no question about it. Now, lanthanum copper oxide was recognized as a Mott insulator from the experimental results very clearly. If you look at C.N.R. Rao Ganguly's work. And also, I will tell you one instant. During that period, one day I returned from a conference and Anderson asked me, what are you excited about? I told him, see, people are worried about a compound. He told me, please don't tell me anything about the compound. Just write down the formula. So I wrote down the formula. So he thought for a while and he said, this should be the structure. I was stuck. That was the structure. Then he thought for a while and he said it should be a ferromagnetic insulator. And that was a puzzle. So what did Anderson do? He did mental simulations and quantum chemistry in his mind. And he essentially concluded in a broad way the right property. So this is what he told me when he came up with the TJ model and the one-band model for cuprate. He said that I relied upon 10 experimental facts rather than the Shanghai singlet theory, which is perturbative and so on. So he enumerated, in fact, I remember 6 of them, maybe at some point I will tell why it should be driven by a single band Hubbard model rather than looking at band theory in detail. So to him, experiments always guided him to the right model. So this is something that I keep telling my young PhD students and friends that please keep looking at experimental results again. It will tell you what is actually going on. Have I answered your question?
Yeah, by and large, yeah. Because I was more interested to know that how, as a theoretician, you would have reconciled without seeing any band structure, basically, of lanthanum copper oxide. Because
if you look at the band structure of lanthanum copper oxide, it's very confusing. So there are so many bands. The copper and oxygen hybridized, And you look at close to Fermi level, there is an isolated band, which is overlapping with other bands. And Anderson's genius was to isolate out that and say, that governs the lower energy physics. So I will stick to not 3-band model, but a 1-band Hubbard model, 1-band PJ. That was the thing. So, these days, LDA community and strong correlation community has become very friendly because we depend on each other. It's extremely useful. For example, some of the work that I did on iron arsenate superconductor use of LDA results, where small energy differences between antiferromagnetic solution, ferromagnetic solutions, and so on gave me some clue about what's going on. Thank you.
Thank you, sir. Thank you.
So some questions from students.
Yeah, can I ask Pankaj? Sorry, students, if you have, I'll finish my question quickly. So
but
thanks.
Tell me in which garden you are in.
This is some simulated background.
Okay.
Because of course my real background is even more interesting, but it's a little bit dark, so you won't be able to see it. Thanks, Professor Baskaran, for a characteristically brilliant talk. And I'm sure we all enjoyed it. And I really enjoyed listening to all those personal anecdotes. And so it's very inspiring. And we really...
It has been my pleasure.
Yeah, we really miss you. And we hope we could have seen you personally here. I'm sure next time we should really invite you over for a long visit. So my question relates to this more is different. So, given the recent excitement in this quantum computing, given that it's gradually getting practically realizable, do you anticipate that this more is different philosophy is going to become less and less relevant? Because once you have a quantum computer, you can pretty much simulate a very realistic quantum system ab initio.
Yeah, that's a very good point. The point is, you may be able to calculate numbers accurately with a quantum computer. The question is, will the quantum computer or the artificial intelligence machine give you concepts? Because we are looking for concepts. That is the key point, because it's the concepts, like if you look at Einstein's theory of specific heat, he realized there is quantumness there in the form of some harmonic oscillators before the beginning of quantum mechanics. Schrodinger's mechanics, he hypothesized. And Planck, looking at experimental results, hypothesized energy quanta and the Planck's constant. So whether a quantum computer will be able to discover that, it will be definitely a good aid. My personal feeling is it's going to be a fantastic aid to take us to a new level. But our mind is, in fact, I believe, is more than a quantum computer. It does wonderful things. I don't comprehend it. So I think it will be complementary, like deep learning algorithms and so on. By the way, I should point out, as this deep learning algorithms are coming, I was 5-6 years ago, I was toying with the idea of the question, can machine discover quantum mechanics given enough data? And it turns out, a young faculty at San Diego, I forget his name, friend of mine from Sinua. So he has written a paper. He has given data about some post-condensation in some random potential. And he is able to construct Schrodinger equation with the right coefficient. So discovering quantum mechanics through machine learning.
Thanks for that, because my latest student is going to be working on machine learning issues in physics. So I have taken a new PhD student. So you please give him your blessings. I hope he's listening.
So the point is, the machine, we can learn a lot from machines. Machine can learn a lot from us, but it's going to be complementary because the simple insight that we have, occasionally inspiration that we get, we don't know where it comes from. Because we constantly think about our subconscious mind is working. So we get insights and inspiration. So personally, I think the best quantum computer will definitely help us. It will help us getting a vaccine immediately, given enough inputs and so on. But I don't know. and maybe it will help us to keep the globe, Earth, from evaporating, the way that we are misusing the Earth and so on. So definitely going to help us if we use things prudently. So this machine, that paper that I has a title called Contemplative Machine. So this is a very nice idea that a machine not only does calculation, but also it thinks about itself. Contemplative machine. So there are beautiful advances, but I believe it will be complementary. We won't become slaves of, unless we decide to become slaves of machines and quantum computers.
Okay, thanks a lot.
Okay.
So questions from students? So Professor Baskaran, you showed us this Anderson garden. The descriptions are given in your article, but can you please elaborate about that for the sake of students?
For the picture of...
Yeah.
This one.
Yeah.
Okay. So let me start with what is there in the sky. You see something in the sky, like a moon or something, that is supposed to be a neutron star. See, Alpar, a bright graduate student at Cambridge, used to talk to Anderson, and David Pines and Ito and others, and with Anderson, said that the glitches one sees in the experiments, because people through radio telescope look at these pulsars and they measure the period very continuously, and occasionally they found out that the periods change suddenly. They are called glitches. So what is the origin of the glitches? So, and there are theories about surface of neutron stars and what it is made up of and so on. And one of the theories is that the crust of neutron star is a superfluid of neutrons. So Anderson was very familiar with vortex lattice in superconductors, real superconductors. And then if you look at the dynamics of vortices, there are lots of glitches. They suddenly get deep in. There's a famous Anderson-Kim theory and so on. So this group of people, Alpar, Anderson, Pines, and Ito, they said these since neutron star is rotating, there are vortex lattices. These vortex lattices, like our continental drift, are moving against each other, and there are occasional star quakes, neutron star quakes. So they modify the period. So this became a very famous theory. So that's how from lab experiment on hot superconductors, you get an insight into working of a neutron star. So that is one picture. That is this picture. Then you see a busy bee zooming. So this is called motional narrowing. It looks like when you, for example, if you are standing close to a railroad, passing train with Doppler effect, you see different frequencies. So Anderson had a theory of motional narrowing. That is, when you look at NMR relaxation, some of these line broadening phenomena gets cancelled because of motion. They get averaged out and you get narrow peak. So that's called motional narrowing. So that part depicts motional narrowing. And then you see a hill-like feature. This is supposed to represent Anderson localization because it's like a mountain which has a peak and tail. It's Anderson localization. Then you see pairs of parallel spins. This is supposed to be the P-wave superfluid in helium-3. Because it turns out there are several phases of superfluid helium-3 as a function of pressure and magnetic field. One is called the Balian-Wertheimer phase, another called Anderson-Morel phase, and so on. So this is one of them. So this was all prediction. Then, of course, it went into pairing in nuclei and up to neutron star. Then this part explains some. Sorry, my cursor is not working well. Do you see my cursor in action?
Yes.
Okay. So this is supposed to, if you look at Anderson's local moment problem, there is some local potential, and then this can be related to some two-level systems. There is a famous Halperin Anderson-Verma theory where in glasses they see some universal feature. Anderson, Halperin, Verma pointed out that there are some two-level systems which are quantum mechanical. They organize to give this behavior. So it could be about the two-level system. And I believe this little bush is a spin glass, and so on. I don't remember. In fact, I don't see what is the meaning of the stream and something going. So I really do not know. So as I said, I contacted several of Anderson's old friends, colleagues who drew this. They all said that, I'm sorry, I didn't do it. So it's for, I think I leave it to students to interpret it more.
Yeah. No, it looks like that some of his friend who was quite familiar with his works drawn this and made it more
so elegant. In fact, I contacted several people. Among them, you may remember the name Dynes, Robert Dynes, who's famous, superconducting experiments, Dynes and so on. Dynes formula. So Bob became a chancellor in California system. I contacted him because I remember Anderson telling me that Bob Dynes could draw this. So Bob said that, I'm sorry, I don't have that kind of ability to draw. So I do not know.
Yeah. So again, students, if you have any query, you can ask this question, because I am telling you that if Professor Baskaran would have been here, then you could have got more opportunity to interact with him. But still, you have this unique opportunity to ask the things.
So let me tell a few words to the students. See, I always find that Indian students particularly don't ask any questions during my colloquium or seminar. But I come out of my lecture room, they crowd around me and start asking questions. So now I don't know how to come there virtually. I wish I could come to your personal home or office and talk to you. That needs quantum computers and maybe teleportation and being there simultaneously in many places. But please don't feel shy. No question is less interesting. I should also tell you, I embarrass the students by saying that if I finish a lecture without any students asking me questions, I feel very bad. That means I have not conveyed what I wanted to say. Please don't leave me with that bad impression about myself.
So, student. Yeah. So, okay. So it seems that they don't have. Much
they can always contact me by email.
Yeah, sure. But still, we had a very nice time by going through all the beautiful theory and about the beautiful journey of a beautiful man. And with this, I would like to again thank Professor Baskaran to accept our invitation and giving us the opportunity to organize this talk on field inertia, and for whom he was closely associated with. And I would also like to thank our technical team for managing it quite nicely. And with this, I would like to announce for the next colloquium that will be on very interesting topic that Professor Baskaran also mentioned, that the next generation topic in condensed matter and optics, that is quantum computation. So that will be given by a very young experimentalist from IIT Kanpur, Professor Shaikat Ghosh, who has recently able to observe this quantum synchronization in his laboratory experiment. So with this, and that talk will be next Wednesday at 4 p.m. again. So with this, I would like to, so there is one question coming from Rajandan. Rajandan, if you are here, you can ask this question before I conclude.
His microphone is not working.
Okay, so I can read his question. He has written the question in the chat box. So, sir, what do you think about India's progress on building quantum computer at present?
To be frank, we should be doing much better. There are very bright people, but we are only beginning to realize that quantum material, quantum computers is important, and government has started spending money. We should have done it 10 years ago, but it's never too late. I'm very happy the government is trying to support it. I should also be frank. See, for the potential that we have, India, we are not spending as much money as we should be spending. Of course, our country is big, we have lots of problems, but still, science is going to save and help society. So we should spend more. That's my humble request. And also, private entrepreneurs should start spending. In fact, it's commendable. Just to give you an example, Krish Gopalakrishnan of Infosys Foundation, he has given 250 crores to start Neuroscience Institute at IIT Bangalore. He has given 60 crores to start 4 chairs at IIT Madras. So there are several billionaires all over India. So billionaires should think about supporting science, because it will not only carry their names, but also it will help society in the long run. I'm fond of giving this example of Maxwell's equation. See, Maxwell synthesized Faraday's law, Ampere's law, Biot-Savart law, and all put together and wrote down a wave equation, which predicted existence of electromagnetic wave and also gave velocity of light, number of the actual value. It was a great surprise. And including Faraday, not many people believed it. 20 years down the line, Hertz discovered it. And then Bose, Marconi connected it. The world is different. So my perimeter, Mike Lazaridis, who's from the Perimeter Institute, is very proud to say that singular discovery of Maxwell's equation alone is sufficient for society to support theoretical physics for centuries, which is true, because you can trace many developments in modern society to things like understanding band structure, understanding band gaps, gave insights into semiconductor physics in the hands of Bodin and others. So many now quantum computers. A deep insight into issues of entanglement and so on is going to revolutionize the future. So I'm very happy that we are beginning to support quantum. For example, if we take IIT Kharagpur, IIT Guwahati, there are so many quantum people, great quantum mechanics, Girish Chetlu, Saurabh, and then experimentalists, and so on. So start a small quantum institute. There is no reason why you should not start. It will be wonderful, actually, because it will attract young people, great engineers. By the way, Grover algorithm, Grover is an engineer, and Peter Shor is an engineer. So engineers are very fond of quantum mechanics. They are good in picking up quantum mechanics and then growing. So anybody can learn quantum mechanics, because after all, it's a set of rules. We don't know why quantum mechanics is the way it is, but it works remarkably well. And it has been very successful. So
Baskaran, so is the money is the only issue, or are we missing something other than investment? Is there, of course, everything, theoretical side, everything is in place. I think a lot is understood already. It's just practically realizing it, isn't it?
No. See, for example, there is a thing called the Majorana fermion, which is very popular these days in the context of topological quantum computation. Now, all over the world, there is so much effort to build Majorana fermion, realize Majorana fermion. I do not know how many efforts are there in India. So we need to put sustained effort on various aspects of nuclear spin. Of course, there are some good people working in NMR quantum computing. But there is something called optical traps and cold atom lattices and Majorana fermion in spin orbit coupled system, thanks to Das Sharma and other people who have theories. Various possibilities are there. So we should put, it's not, I think it's money plus other things. But money is very important. We have to invest money. I think it's, and a place like IIT, you have very well endowed alumni. Please catch them, and they'll be more than happy to contribute if you convince them. I'll be very happy to join you in convincing them.
That would be really nice.
Yeah, I think we should, departmental level, we should start some kind of a committee and decide how to attract private funding into the department. I think we are not doing that. Write to all these big, corporate houses like Ambani I mean, they have too much money, they don't know what to do with it. So you tell them that you will build a quantum computer, it will help Reliance. So I am sure...
No. See, it's more than that, because, for example, Mike Lazaridis, I had the opportunity to meet him because I was part of International Review Committee. So there I had an opportunity to talk to him for 20 minutes. He's so passionate about theoretical physics. He doesn't want immediate rewards. He knows that maybe 100 years down the line, or 20 years, there will be a great service to humanity. I think that many people have that attitude, like Krish Gopalakrishnan, or in Chennai, A.C. Muthia Chettiar, who founded this SPIC Science Foundation, SPIC Mathematics Foundation. So they're very passionate about science. They don't want immediate rewards. So there are many enlightened people. I think you bright people can convince your own alumni. I'm sure it's a question of networking with them. Sorry, I'm talking too much. Yeah.
No, it was very nice. So with this, I thank you all for actively participating in this talk and hope same kind of participation for the future series of talks also. So with this, I thank Professor Baskaran and we wish you...
I take this opportunity to say hello to many friends,
Yeah.
Saurabh Basu, Pankaj and Srinivas and many friends. I'm sorry, I don't remember the name immediately because I've been there a couple of times. And also thanks to Pasad Vijay for technical help. So wonderful. Thank you very much. And I hope to see you personally there and interact. So at that time, students will ask me many questions.
Thank you very much. Thanks a lot.
Yeah, thank you.
Thank you, sir. So we say goodbye.
Goodbye.
Bye, sir.